When are we going to be able to see the homework solutions? So I usually post the solutions after I grade them. So actually, I do plan on grading them today. I've set aside time in my schedule to grade. And so probably by the end of the day, today, you'll see the solutions. Normally, when I grade stuff, it usually takes me about a week after you guys turn it in or after the due date. And so at the latest, it'll be a week after. Yeah. So, 8:30. Let's go ahead and get started. Good morning, everyone. How's everyone doing today? Okay. We're tired. Yeah, I know. I feel bad. I'm like always tired for this class because I have kind of a late shift on Mondays and Wednesdays, and then I go home, I eat something, I shower really quick, I go to sleep. I never get enough sleep, and so I'm always like really tired when I come to the class. So I apologize if I ever sleep before. I always try my best, to bring energy, but sometimes the sleep just isn't there. Okay, so we're at the start of week 3. And so we're right in the middle of our ordinary differential equations review. Right? So last week on Thursday, we started with the second order differential equations. Okay? So we're going to continue with that discussion today. We're going to talk about some applications today, which I think is exciting. And so we're going to talk about the mass spring damper. Maybe you've seen it already, but it's always good to kind of look at it again, because the mass spring damper, I think, surprisingly, is actually one of the more important physical systems to understand. You can actually apply it to a lot of different systems. Okay, so we'll talk about that today. And what I'm hoping today is that we also get talking about some non-homogeneous ODEs. Okay, so we're going to review, hopefully review the method of undetermined coefficients. All right, so some announcements. So homework 2 has been posted, so that is on Canvas, and so I'm not sure if Canvas notifies you whenever I post an assignment, but homework 2 is up. It's all about second order ODEs, and so it's basically covering everything we did last week and everything we're doing this week. And the due date for homework 2 is going to be not this Friday, but next Friday. So you guys have about 12 days. About 12 days to work. Okay, so I think that's all my announcements. Homework 2 is a little bit lengthier than homework 1, so I would definitely recommend looking at it now. So I think as of right now, you should have enough information to do just about 60% of it, and so and then by the end of this week, you should have everything you need. So definitely take a look because it is going to take you longer than homework 1. I know for myself, I think my solution for homework 2 was about 7 pages, whereas my solution for homework 1 was about 4 times. Yeah, it is. All right. Any questions on, on anything before we begin today? Okay. All right, so let's go and get started. And so the first, our first topic today is going to be the mass spring damper system. Okay. So up until this point, we've been talking about ordinary differential equations, and in particular, we're focusing on second order differential equations. Second order equations are actually very applicable to a lot of physical systems. One of which is the mass spring damper, which is something that's very important for if you're a mechanical engineer, civil engineer, work with anything that can vibrate, basically. A mass spring damper, you can use it to model its behavior. And so a mass spring damper physically looks like this. And so we have a spring. And so the spring has a spring constant K. Remember, the spring constant K, the typical units for this is SI, or Newton per meter. So basically, the spring constant tells you how much force the spring is going to exert, depending on how much you stretch it or compress it. We have a mass, M. We all know the SI units for mass, so mass is just a kilogram. So, this mass can represent a lot of things, depending on the system you're looking at. But I think in the simplest case, this mass is I think of it as just like a wooden block or like a metal block. And that's visually kind of what it looks like. And then the last thing that we have is, something that's hardest to visualize, but oftentimes it doesn't take this kind of specific form, but visually we kind of just represent it like this, and that is the dash pot. Okay? And so the dash pot represents some kind of dampening agent. So any kind of friction or any kind of air resistance, that's kind of what this kind of represents. So it's hard to draw friction, it's hard to draw air resistance. So oftentimes the way that we draw it is a plunger in water. So that kind of gives you the same. Let's know that. And this damping constant B, its units are oftentimes a force Newton over velocity. Okay. So Newton per meter per second. Okay. All right, so that's our mass spring damper system. So that's kind of physically what each of the terms mean. This is kind of the simplest form, but you'll see that we can apply this to a lot of systems. In particular, we're going to look at a motorcycle suspension, which is going to be our main example for today. All right, so first, before we look at the equation, let's talk about what's going to happen physically. So, usually the way that you set this system in motion is that you take the mass, you kind of displace it a little bit, so you kind of pull it away from its equilibrium position, and you let it go. And so, just first, kind of for simplicity's purpose, let's just look at the mass spring. Okay. I think that's a little bit easier to start with, and then we'll bring the damper back in later. And so for the mass spring, what's going to happen is that when you, according to Hooke's law says that if you displace a spring from its equilibrium position, there's going to be a restoring force. And so according to Hooke's law, this restoring force F is going to be minus K, the spring constant, multiplied by X, where X is the amount that you displace the mass. And of course, the negative sign means that it's a restoring force. Okay? So anytime you displace a spring is very much like I call it like I draw the analogy, it's like an introvert. So an introvert always likes its own comfort zone. Like me, I like to be home and play video games and not talk to people if I don't have to. So anytime you pull an introvert away from their safe zone, they want to just go back. And so springs are kind of the same way. And so you pull a spring, you stretch it, and compress it, it wants to go back to its equilibrium. That's why we have a negative out there to indicate that it's a restoring. Okay. All right. So that's the restoring force that we're working with. If we equate this to Newton's laws of motion, we know that the sum of the forces on an object are equal to its mass times acceleration. And if you draw a free-body diagram around the mass up there, you'll see that the only force that's being applied to it is just the spring force. And so if we say that minus kx is equal to the mass times the acceleration. Let's go ahead and move kx to the other side, just so it's all kind of all positive signs. Okay, so we have 0 equal to mass times acceleration plus kx. Okay. And I'm going to do one more thing. And so we know that the acceleration and the displacement of an object are related in terms of derivatives, right? And so one way that we can represent the acceleration. Okay, one way that we can represent the acceleration is as the double derivative with respect to time of the position. Okay. And so if we put this all together, we get the kind of the simplest differential equation that we can for a mass spring system, which is that the mass times the second order derivative of the position plus a times the position equal to okay. And that is going to be our governing equation. The good thing here is that since our governing equation here is a second order differential equation, it looks almost exactly like the equation that we were solving last week, both because it has constant coefficients, right? we're going to be able to solve this using our methods that we learned from last week. All right. Any questions on this? Okay. All right. So let's go ahead and solve this. Okay. And so if we solve this equation, let's also take note that our coefficients in this case, the mass and the spring constant, both of these are going to be positive, right? So there's no such thing as a negative mass, as far as I'm aware of. This might tell me differently, but everything that has to have a positive mass and spring constant, the way that we define it, is also positive as well. And so we know that kind of already in this equation. Even though they're variables, we can already kind of say that these are going to be positive numbers. And so let's do the same thing we did last week. So let's go ahead and form the characteristic equation. Okay. So the characteristic equation here is m lambda squared plus k 0. Okay. I'm gonna work on this algebraic a little bit. So I'm gonna divide both sides by m, and I'm gonna move the k to the other side. And so if we do that, we get lambda squared is equal to minus k over m. This tells us that lambda, if we take the square root of both sides, is equal to plus or minus square root k over m times I. Right. Because we had the square root of a negative number, and so square root of -1 is just I. And so since our lambdas here, or since the roots of our characteristic equation here are imaginary numbers, we know that we have complex conjugate roots. So this is case 3 from our 3 cases from before. And so that tells us that our solution x of t is equal to a cosine time of square root k over m t plus b sine square root of k over m times t. So it's basically just a sinusoid. And so, because there's no damping in the system, we don't have any decaying coefficients. And so what this tells us is that if you have a mass spring system with no damping, no friction, no air resistance, it's just going to keep oscillating forever. Okay. We don't even have to solve for the coefficients. We don't even have to apply initial conditions. And so just by looking at the form of the solution, by looking at the functional form, we know that this is going to give us infinite oscillations. Okay. So we graph it. Might look something like this. Okay. And so it's just going to keep oscillating for infinite. There's a couple more pieces of trivia. And so when you have infinite oscillations like this, another word that people, or another term that people call this is called harmonic motion. Okay. And so if you ever hear that term harmonic motion, all it means is it's just referring to infinite oscillations. Okay. And the frequency of these oscillations Okay. If you notice, both the sine and cosine terms have the same frequency, so they have the same term that's in front of the t. Okay, and so the frequency of these oscillations is a. And oftentimes sometimes we call this omega naught, which is called the natural frequency. We'll talk more about natural frequency on Thursday. And so on Thursday, we'll talk about the idea of resonance. But just know that, whenever you have a physical system, even not even just mass spring dampers, it could be anything. There's a natural frequency that it likes to vibrate at, that it likes to oscillate. If you play a musical instrument, if you play guitar or something, you're very familiar with this. And so you'll know that, on a guitar, if you pluck one of the strings, it plays a certain sound. And the sound that it plays is basically the natural frequency of that string, which depends on the length of the string and the tension that's in the string as well. Okay. If you've ever swung on a swing in a playground, you'll understand that as well. And so, that, based on the length of the swing and how heavy you are, okay, there's a natural frequency at which, you kind of ride on the swing. If you want to kind of increase your oscillations or to go higher, you have to apply force that's in rhythm with that frequency. Okay. So every system has its own natural frequency, and that's usually based on the physical characteristics of that system. Okay. Any questions on this? Okay. Okay. So that's the undamped system. So that's when we have just the mass and the spring. Okay? So we get very interesting behavior, but also not realistic. So we don't often see things oscillating for infinity. Okay? So let's introduce some damping. So what's interesting about the damping, and I think this is probably usually the part that's not talked about a lot in previous courses. And so the damping, the way that it works is that it scales based on the velocity of the system. And so basically, the faster you're going, the faster your velocity, the more damping that you experience. And so the force for the damping is equal to minus V times V. Remember, V here is our damping constant. And V is our velocity. Okay. And so if we replace this, we're going to basically factor this into our force balance in order to get a differential equation. Then our damping force is going to be minus V times the first derivative of the displacement. Okay, so we have a minus V dx dt. Okay, so let's add this to our force balance from above. And so we know that we already have a spring force that's being applied onto the mass. Okay? And so if we sum up all the forces on the mass, we first get the spring constant, spring force. And so we know the spring force is minus kx. Okay. Now we're going to add our damping force. And so we're going to add our damping force to this. So that's our second force. And then according to Newton's second law, all of this is going to be equal to the mass multiplied by the acceleration of the object. So mass times e squared x. T. Okay. All right, so let's move some stuff around just so that we get everything kind of on the same side of the equation. And so if we move some things around here, we get m e squared x dt squared plus d dx dt plus ax. And this right here is our governing differential equation for the damped mass spring damper system. And so just like last week, what you'll see here is that we have a second order differential equation. Here we have all three terms, and so we have the second order derivative term, the first order derivative, and just the regular term. Okay. And so just like last week, we're going to have three different cases. And so depending on the roots of the characteristic equation, that's going to give us three different types of solutions. All right, so let's review, what those three cases are, and then we'll kind of talk about physically what that means. Let me write first three different types of solutions. Okay. All right, and so just like any second order differential equation, this is a homogeneous system. We're going to form the characteristic equation, and then based on the roots of that equation, we're going to have three different cases. All right, so let's look at case one. So case one was the simplest case. This is when we have two real roots. Okay. And so physically, for a mass spring damper system, if you have two real roots, what we call this kind of system is we call it overdamping. And so the reason this occurs is because the damping constant B is very large. And so when you have a very large damping constant, then that causes your system to have two real roots. And if you remember what our solution looked like from last week, so when we have two real roots, our solution just looked like a decaying exponential. Okay? And so visually it looks like this. And so visually you don't actually get any oscillations at all. Okay, and so if we plot our solution, x of t on the vertical axis and t on the horizontal axis, it would look just like this. You get no oscillation. So you may excite the system, you may kind of displace it, but because the damping is so high, like the friction or the air resistance is so high, the mass just kind of returns to its equilibrium position without without any oscillation. So not too exciting. But sometimes you want this, and especially if you're looking at the suspension system in a vehicle or a motorcycle, which we'll talk about soon. This is something that you actually want, because if you're riding a car and you go over a speed bump, you don't want to be like you want the system to just kind of damp down and make sure you're comfortable with it. Sometimes this is preferable, but it's not too simple. All right, so then we have case two. So case two is our repeated root. And so for repeated root, we call this critical damping. And so critical damping, visually it looks very similar to case one, because if you remember what our solution looked like, we still had that decaying exponential. Okay. The only difference is that our second solution had that extra T. Okay? And so if you kind of plot the solution, it would look very similar. So it would look kind of like. And so again, we have no oscillation. Okay. But what's interesting about the critical damping is that if you kind of compare, and I kind of tried to draw it like it, although I wasn't super successful. But if you have critical damping, what's unique about the system is that it actually decays to zero faster than overdamping. It's a little bit paradoxical, because you would think that the more damping that you would add in, it would actually it should decay down to zero faster, but that's not actually the case. And so if your goal was just to reduce any kind of excitement as quickly as possible, you actually want to be in the critical damping, because this decay rate right here is the steepest for critical damping. And the reason for that is because in critical damping, remember, the roots of our characteristic equation are the same. And so both our complex exponentials are going to decay at the same rate for the repeated root. Okay. When you have overdamping, what tends to happen is that we have one root that decays really quickly, but the other root may not decay as quickly. Okay. And so for overdamping, if you've ever gone shopping for like a buy one get one deal, usually the restaurant's going to charge you for the more expensive one and then give you the cheaper one for free. So that's kind of the same thing with overdamping. It's kind of determined by the slowest process. Okay, and of course we have our third case, which is our complex conjugate roots. And so when you have complex conjugate roots, this occurs when your damping is not high enough. And so we call this underdamping. And so this is kind of the last case I think we talked about kind of at the very end of class on Thursday. And so in these cases, you do have oscillations, and so the sine and cosine terms are there, but you have a decaying magnitude. And so visually, what it looks like is that it looks like kind of a decaying sinusoid. And so you may have a solution that starts oscillating early on. But because the damping is present in the system, eventually these oscillations are going to die down. Okay. And so in these situations, the damping is there, but it's not enough to stop the oscillations from occurring. So you still see oscillations, but eventually they are going to die down. All right, any questions on any of this? Okay, so let's apply these in an example. Okay. And so like I mentioned before, mass spring damper systems are used to model a lot of physical systems. One great example of this is the suspension system in your car. If you ride a motorcycle, the suspension system in motion. And so if you're not familiar for what, with what the suspension system does, another name for it, I think people call it or the shock absorbers, okay? And so when, usually when you're riding a car, and you're driving over the road, there's a lot of bumps and cracks and speed bumps that you're going over, right? And so kind of the purpose of the shock absorbers is to kind of take these kinds of excitations, okay? And kind of smooth them out so that you as a rider, you as a passenger or a driver, you don't really feel these oscillations. Of course, you might feel them initially when you first go over them. But then what the purpose of the suspension system is to try to make it so that it smooths it out. So, the ride is as comfortable as possible. Right. So visually, I know it's a lot more complicated than this, but just for the sake of this class, let's visualize it like this. And so, let's say that this rectangle here is the frame of your car. Okay. Here we have your wheel. Okay. Your oblong shaped wheel. Okay. I know this. I remember in high school, my geometry teacher, he would always draw perfect circles, and then he said his secret is you have to put your hips into it. So every time he drew a circle, he kind of did this whole kind of motion, and it worked. So no one could really make fun of him because he drew beautiful circles, and everyone was really jealous of him. Okay, and so your suspension system basically attaches to it doesn't attach directly to the wheel, but for now we'll kind of assume that it does so. And so the suspension system, kind of visually, you can kind of think of it as two different components. And so let me kind of draw it. And so there's the spring components, okay? So there has to be a spring. Okay? And then there's also kind of a dash pot that's attached to it as well. So, kind of forms a perfect kind of mass spring damper system. Okay? Where the mass in this case, we're going to consider the mass of the wheel, okay? The spring is usually kind of a massive spring as part of the suspension system. So we'll give that the spring constant K. And then there's a lot of damping in the system as well, introduced by the suspension system, which we'll model with a damping constant. Right. And so here we have kind of a very kind of traditional mass spring damper. So we know that the governing equation for this I'm going to use the symbol Y. Okay, so Y here is going to be the vertical displacement of the wheel. And so the governing equation is going to be m d squared y dt squared plus b dy dt plus ky to 0. So let's plug in some numbers here, some typical numbers that you will see for modeling suspension systems. So let's say the mass in this case is 12 pounds, and so we're going to use English units here. Okay. The spring constant B is going to be 240 pound per feet per second. Okay. And the spring constant K is 1152 pound per feet. All right, so let's plug these numbers in. So we have 12 d squared y t squared plus 240 e plus 11.2 y is equal to 0. Okay. All right, so that's the governing equation, and so let's solve for a couple of things here. And so let's solve for. So let's answer the following questions. And so in part A, let's just simply characterize the solution, okay? And so based on the roots of the characteristic equation, before we even form the solution, we can characterize the system as overdamped, underdamped, or critically damped. Characterize the solution. Let's solve for the homogeneous solution, or solve for the general solution. And then in part C, we're going to solve for the particular solution or the specific solution for the case when we are going to have this car run over a speed bump. And so the way that we're going to model the a speed bump is that, initially when you first hit a speed bump, your wheel is still going to be on the ground, but as the car kind of hits the speed bump, it's going to have a velocity going up. Okay. And so we're going to give this wheel kind of an initial upward velocity. And so the way we're going to model that is going to say dy dt at t is equal to 0. We'll say it's equal to 10 feet per second. Okay. And y at t is equal to 0. We're just going to assume it's 0. And so at the exact moment that the wheel strikes the speed bump, it's still going to be on the ground. It's not going to accelerate upwards yet, but it is going to have an initial velocity. So the initial position is going to be 0, but we're going to give it an initial velocity. Okay. All right. Any questions on this, the setup of this problem? Okay. All right. So let's go ahead and start solving it. So let's start with part A. Okay, so part A is asking us to characterize a solution. So let's go ahead and form the characteristic equation. Okay. And so let's take the coefficients of our governing equation here, and then let's make it a quadratic equation. Okay. So our characteristic equation here is going to be 12 lambda squared plus 240 lambda plus 1152. All this is going to be equal to 0. Okay. All right. So now that we have this quadratic equation, we can solve for the roots. And so I think the easiest way to do this is with the quadratic formula, just because the numbers are pretty a little bit insane here. Right? So I'll go ahead and skip those details. So I'll go ahead and assume that you can plug into the quadratic equation, quadratic formula. And so we actually get two real roots here. So we get lambda 1. Lambda 1 is equal to -8. And lambda 2 is equal to minus. And so we look back at our categories from earlier. We know that if we have two real roots, then that means that this system is going to be overdamped. And so that's going to be part A. So part A, we found the roots of the characteristic equation. We saw that there are two real distinct roots. And so that tells us our system is overdamped. Okay, so that's part A. Let's move on to part B. So part B is, of course, going to be the general solution. Okay. And so the general solution, all we have to do is just plug in these two real roots. So, we have our solution one, y1 is going to be e to the minus 8t, y2 is going to be e to the minus 12t. Okay. Based on the two roots of our characteristic equation. And so if we combine these together, we take a linear combination of these two solutions and get yt 2 a e to the minus 8t plus b e to the minus 12. Okay, and so finally, let's do part C. So let's go ahead and apply our initial conditions. All right, so we have two initial conditions here. And so if we look back at the problem statement, we have an initial condition on the velocity. And so our initial velocity is going to be 10 feet per second. And we have an initial condition on the position, which is just we start from a rest position. Okay. And so we know that our first initial condition is dy dt at t is equal to 0 equal to 10. Okay. So let's form an equation for this first. So let's take the derivative. So dy dt. So I'm going to take our solution here and take its derivatives. We have minus 8a e to the minus 8t minus 12b e to the minus 12t. Okay. Let's plug in t is equal to 0. And so we're plugging t is equal to 0 into this. Both the exponential terms are going to go away because we have e to the 0. And we know that e to the 0 is just 1. Right? So dy dt at t is equal to 0, it's going to be minus 8a. Excuse me, minus 12b. And we know this is going to be equal to 10, okay, 10 feet per second. So that's our first equation. We're not able to solve it just yet because we have two unknowns here. So let's go ahead and combine it with our second initial condition. Y of 0 is equal to 0. And so if we take our solution up here and we plug in 0, both the exponential terms are going to go away. And so we get 0 is equal to a plus b. Okay. And so what we have here are two algebraic equations to solve for our two unknowns a and b. Okay. Right. And so we can go ahead and solve these equations for a and b. Okay. You can do this any number of ways. One, I think the easiest way to do it is to start with the second equation. Okay. And so if we solve the second equation for a, we see that a is equal to minus b, right? And so we plug that back into the first equation, and then you use that to solve for b. Okay. But you can do this, however you want, whatever you think is best. And so we solve for these coefficients, and what we get is a is equal to 5 over 2, and b is equal to minus 5. Right. And so let's go ahead and plug this into our final solution. You get y of t equal to 5 over 2 e to the minus 8t minus 5 over 2 e to the minus 12. Let me show you the graph of the solution just so that you can see it. And so when you run over a speed bump with your car, you would initially expect to have some discomfort, right? And so when you go over the speed bump, it's going to produce initial velocity and you're going to kind of feel that in your car. You're going to kind of hop up. And so because of the initial velocity, you actually see that in the solution. And so we actually see, it kind of goes up like this. Okay. So that's you going over the speed bump. And so, you're going to have your car going to have a vertical displacement. But because of your shock absorbers, and in this case, the shock absorbers are in pretty good condition, that initial discomfort kind of quickly goes away. So we can say shocks. And so the bump or the speed bump is quickly damped away. And so in your homework, I'm one of the problems on the homework is going to be question.
So if shocks that are not in good condition would be like more oscillation?
Exactly, right. Yes. Yeah, and that's exactly what I have you look at in the homework. So one of the problems in the homework, I'm going to have you model kind of a very common test that you can use for your shock absorbers. Okay? And the main thing that you're going to see, if you kind of compare the coefficients here, okay, the values of A or M, E, and K, okay, you'll see that the value for B on the homework problem is going to be lower. Okay? And so that's kind of the first thing to go. When you have a shock absorber or a suspension system that starts to deteriorate, it's not able to damp these oscillations away. Okay, and so I'm going to have you model that. So you're going to look at a suspension system that's not in very good condition, and then based on the solution that you get, you can make a recommendation to this person, whether they should replace their shock absorbers or maybe they can keep them for another year or so. Okay. All right, any questions on this example here? Okay. All right, and so that's mass spring dampers, and so there's a plethora of information that we can go over with mass spring dampers, and there's a lot we can do. But we do have to move on, and so I do want to finish up our ODE review by the end of this week, and so to do that, we have to start talking about non-homogeneous ODEs. Okay. So everything we've considered up to this point for all the second order ODEs have been homogeneous. And so what that basically means is that, we have all our derivative terms, but the right-hand side of the equation has been 0. Okay. So now we're going to kind of lift that assumption and we're going to start to look at cases when the right-hand side is not equal to 0. Okay. So we go back to kind of our standard form for the second order differential equation. It looks like the following. Right. And so what I've written so far is kind of what we've been working with. So it's a second order linear differential equation with constant coefficients. Okay, so P and Q are constants. Okay. Up until this point, we've only considered cases where we set this equal to 0. But now we're going to look at cases where this is going to be equal to some functions, R of X. Right? And so this function, or I should say the presence of this function, makes our equation non-homogeneous. If you recall from, I think we probably last Tuesday when we talked about this, this is often called the forcing term, or the input term. Those are usually the names that we call. Okay. And so of course, because we're changing the equation, so we're adding this additional term here, the nature of our solutions are going to be different as well. Okay. Okay. The nice thing about this, and this is primarily due to the fact that our equation is linear and constant coefficients, we can basically treat the presence of this term almost separately from the rest of the equation. Okay. And so now our solution kind of has two components. Or say two parts. And so our y of x, or our y of t, okay, or y of t here is kind of the full solution, and so this is the solution to the entire equation, is now going to be comprised of two. And so the first part, I'm going to call it yh of t. So this yh of t is the solution to the homogeneous part of the equation. And so we'll call this the homogeneous solution. And so the homogeneous solution is basically everything that we've been doing up to this point. And so you basically set the entire left-hand side equal to 0. You form the characteristic equation, you find the roots, and then you form the solution based on that. So the homogeneous part is exactly the same. And the good thing is that that part shouldn't change at all. Homogeneous solution, this is. So the nice thing about, adding the non-homogeneous term is that, part of the solution is just kind of do the same thing as we've done before. And so that part doesn't change. What is going to change is that we're going to add an additional solution to this. Okay? And so this additional solution, and I realize I'm kind of reusing this term a bit. So, I kind of wish I didn't call it this before. But this term right here is called a particular solution. It actually has nothing to do with the initial conditions. And so the particular solution, this is the particular solution to the non-homogeneous part, or so to the forcing term or the input term. And so we're almost going to solve the non-homogeneous part kind of separately from the homogeneous part. Okay. And so to solve kind of a fully non-homogeneous second order differential equation, basically you would do it in two steps. So the first step you would do is you would solve the homogeneous part. Okay. So that's everything that we've done before. So you basically take your equation, you pretend R of X is equal to 0, and you solve it just as normal. Okay. That'll form your homogeneous solution. And then after that, step 2 is to solve for the particular solution to the non-homogeneous part. Okay. First, solve genius part Okay. So that's always the first step. So whether you have a non-homogeneous term or not, okay, first step, always form the characteristic equation, set it equal to 0, and solve for the roots. Okay. The next step is going to solve for the particular solution. We don't know how to do that yet, and so that's what we're going to learn new. Okay, so step 2 here is kind of a new thing that we're going to learn. Okay. Then once you find the homogeneous solution and the particular solution, you're just going to simply add them together, okay, to form the final solution or the full solution. And then finally, the last thing that you do, if you're given these, is to apply the initial conditions on the full solution. Okay. That's kind of your game plan for attacking these kinds of. So the last step is key. And so when you're given initial conditions to a non-homogeneous problem, I think what some people tend to do is that they apply the initial conditions to just the homogeneous part, and then they get the coefficients, and then they add the particular solution to that. But that's actually not good. You need to solve for the particular solution first, add it together with the homogeneous solution, then apply the initial condition on them together. Okay, so make sure you be careful about that. All right. And so the rest of class today, and then what we're going to focus on a lot on Thursday is how do we solve for these kind of particular solutions. Okay. There's actually two methods, or two main methods that I learned when I was in school. And so because of the time constraint for this class, we'll only have time just to cover one of the methods, and that's called undetermined coefficients. Okay. The other method called variation of parameters, it's more flexible, but it's also much more pain in the ass. And so we're just going to do undetermined coefficients. All right, any questions on this so far? Okay, all right, so let's talk about undetermined coefficients. All right, so undetermined coefficients, it almost feels bad calling this like an actual method because it's more of a trick than anything else. Okay. And so the idea with undetermined coefficients is the fact that if your non-homogeneous term, so if your R of X takes a particular form, then what we can do is we can guess that the particular solution will look like that form. And so for this, we're kind of relying on the fact that, whatever our particular solution is going to look the same as our forcing term. Okay. And so there's kind of four well, three classes of functions that we can solve with undetermined coefficients. First is an exponential function. Next is a polynomial. Third is a sinusoid. Okay. So these are the three types of functions that we can do. And the reason it works for these three is that if you take the derivative of these functions, you end up with another function that looks similar to the original function. Right. So I think the most classic case for this is an exponential. Okay. You take a derivative of an exponential function, you get the exponential function. Okay. Same thing with sinusoid. So you take a derivative of sine, you get cosine. You take a derivative of cosine, you get sine. So you kind of repeating the same kind of two functions. Polynomial is the one where it's a little bit of a stretch, but the idea is that you take a derivative of a polynomial. So you take a derivative of like 3x squared. Okay. You take the derivative of that, you get another polynomial. It's granted it's a polynomial of lower order, but it's still a polynomial. Okay. All right. And so I'm going to give you kind of the forms for these. And so if your R of t, or if your forcing term has an exponential form, say it's e to the lambda t, that means your particular solution is also going to be e to the lambda t. Okay. And so it's going to be an exponential with the same coefficient. The only difference is that we don't know what that coefficient is going to be. Okay. So it's going to be an exponential with the same kind of power, but the coefficient in front is what we need to determine. The polynomial one is probably actually the most complicated. And so let's say if you have a polynomial and so it has certain power n, okay, what we need to do is that our guess for the particular solution is going to be a polynomial that starts with the same order, but it also includes all of the lower order polynomials as well. Okay. And so we have yp equals a x n plus b x n minus 1 plus c x n minus 2, dot, dot, dot. Okay. And so even if your forcing function is just one polynomial term, so let's say it's just x cubed, right? Even if it's just x cubed, then our guess for the particular solution has to have the x cubed and all of the lower order terms as well. So it has to be x cubed, x squared, x, and the constant. Okay? And you have to plug, we're going to plug all of those back. I said RT, but I used x. Okay. All right, so finally for a sinusoid, and so if you have any sinusoid in the solution, whether it be sine or cosine, or maybe both, your guess for the particular solution has to include both sine and the cosine. Okay. And so And so kind of very similar to the polynomial. So no matter if you have just a sine or just a cosine, your guess for the particular solution has to include both sine and cosine. Okay. The only thing that you have to make sure of is that the frequency that you choose for your particular solution is the same frequency as the guess or as the forcing. Okay. All right, so that kind of summarizes all the rules. So I know, this is not kind of the neatest way to put it, and actually I didn't plan to share all the rules till later, but I thought I'd share them all now. And then, just for today and for I think probably the first half of Thursday, we'll just focus on just doing examples. Okay. Because I think with these undetermined coefficients is that, it's useful to have the rules kind of stated out like this, but in order to really get used to it, you just kind of need to see just a bunch of examples. So, I think we'll have time for one example today. And then I have two more examples for Thursday. And then by then, we'll start to see kind of, how this method works. Did you go over undetermined coefficients in math? Okay, so this should be familiar for. All right, any questions on this before we jump into an example? Okay, all right, so let's do one example kind of quickly before we okay, and so this example, let's have a no damp system. So we're going to have y double prime plus y. And this is going to be equal to 0.001 x squared. Okay, so we have a non-homogeneous equation because we have a term on the right-hand side. And so for this problem, I don't think I have initial conditions. Okay, so let's just solve for the full solution. And so in this case, we're not given any initial conditions, and so we're just going to leave it in terms of the arbitrary constants. But that's okay. And so the main point of this example was to look at the undetermined coefficient. All right. Well, before we do that, let's go ahead and solve the homogeneous part of the equation. Okay, so a homogeneous problem, we're going to take all the y terms. We're going to set it equal to 0. Okay, so we're basically going to ignore the non-homogeneous term at first. And we're going to solve for a solution. So we have y double prime plus y. Okay. And so if we form the characteristic equation for this, we have lambda squared plus 1 is equal to 0. Okay. We solve for lambda. See that lambda in this case is plus or minus I, because we take 1 to the other side, we take the square root. And so that's square root of minus 1. And so we know square root of minus 1 is I. Okay. And so of course, this means we have complex conjugate roots. And complex conjugate roots means that our solution is just a sine x plus b sine x. Y homogeneous. Okay. In step 2, now we're going to start to solve for the particular solution. And so our guess for the particular solution is going to be based on the form of the forcing function. Okay. And so in this case, our forcing function is a simple quadratic, so 0.001 x squared. Okay. And so we go up to rule 2 right here. This is obviously a polynomial. That means our guess for the particular solution is also going to be a polynomial. We have yp of x. Let me use a different message here. We'll call this C1 x squared. Okay. So we have to include x squared because our forcing function is x squared. But since it's a polynomial, we also have to include all the lower order polynomials. We have plus C1 x plus P2. Okay. And so for a quadratic function, we have to include the quadratic term, the linear term, and the constant term. All right, so that's our guess. And so the next step is to take derivatives of our guess. and plug it back in. Okay. So let's take the first derivative of yp. Okay. And so the first derivative of yp, we have 2 c1x plus c1 twice. C. Okay, great. Sorry about that. So yp of x is c1x squared plus c2x plus c3. Sorry about that. Yeah, so there should be three unknown constants. All right, so we take the derivative of the new yp, and so yp prime is going to be 2 c1x plus c2. Okay. C3 goes away because it's just a constant, right? So take the derivative of a constant goes away. Okay. We're going to take one more derivative because we need to plug in, for the second order derivative here. And so we take one more derivative here, we get 2c1. Okay. And then c2 goes away because it's just a constant. All right, so let's take these and this, plug it in. Let me write out our original equation again. So our original equation is y prime plus y equal to 0.001x squared. I should really have practice. Okay. Let's go ahead and plug this in. So we have y double prime. So y double prime is 2c1. Okay. Then we have plus y, and so we actually don't have any first order derivatives here, so we can ignore kind of yp prime. Okay. So let's go ahead and plug in our guess for yp. And so yp is c1 x squared plus c2x plus c3. And this is equal to 0.001x squared. Okay. Our next step, once we reach here, is to group like terms. And so we're going to group terms with the same power of x together. Okay. And so we have the x squared terms. We have c1 x squared. Okay. Plus, then we have the x terms. We just have one of them. So we have plus c2x. And then we have the constant terms. So the constant terms are 2 c1 plus c3. Okay. And all that's equal to 0.001 x squared. All right, and then the last step, now that we've set up this equation, we've grouped the like terms. Okay. The last step is to solve for the values of the coefficients, C1, C2, C3, using the like terms on the left-hand side and the right-hand side. Okay. So I usually like to do it like this. And so, for a polynomial, we have 3 terms that we're considering. Okay. We have the x squared term, we have the x term, and the constant. Okay. And so what I'm going to do is I'm going to set up a system of equations based on the equality on the left and right side. Okay. Right. So I'll give you an example. So for the first one, we have c1 x squared on the left, and on the right hand side we look and see what the x squared term there is. 0.1. Okay. Next, we do the x term, and so the x term on the left hand side has c2. And on the right hand side, we have no x term over there, and so we're going to set that equal to 0. Okay. And then for the constant term, on the left-hand side, we have 2C1 plus C3. And on the right-hand side, we have 0. Okay. Even though it's 3 equations, 3 unknowns, usually these systems are not too hard to solve. Okay. So I'm going to go just a little bit quickly, just because we are out of time today. Okay. And so if we plug in for this, we get C1 is equal to 0.001, C2 is equal to 0, and C3 is equal to minus 0.002. Okay. And so we plug all this in, we get YP is equal to 0.001 x squared minus 0.002. Okay. And so our full solution y of x is going to be YH plus YP. Okay. And so we put it all together, we have A cosine x plus B sine x plus 0.001 x squared minus 0.00. Any final questions on this example? We're kind of still writing it down. Okay. All right. So I'll leave this up for a bit. If you're still writing it down, I'll stick around a bit after class if you have questions. So thank you guys for coming today. I apologize for going over bits. Usually I try not to do this, but I wanted to make sure I finished doing it. And so Thursday, we're going to pick this up again. We're going to do a couple more examples with undetermined coefficients. And then we'll talk about the last concept that we have for second order ODEs, which is resonance. Okay. All right. I hope you guys have a good rest of your day. And I'll see you guys all on Thursday. Right here. Oh.